Hello, this is video for lesson 6.4, the last section for chapter 6. Excuse me. It is called Determinants and Cramer's Rule, yet another way to solve systems of linear equations. So far, if we're keeping track, in chapter 5, we learned how to solve linear systems using substitution and elimination. Then in chapter 6, we learned how to use a matrix to solve a system of linear equations using Gaussian elimination in 6.1, and then matrix equations in 6.3. And now finally, we have another way called Cramer's rule that uses what's called a determinant to solve systems of equations. So we have lots of options. So the first learning target there, we're going to find the determinant of a square matrix 2 by 2. Then we're going to learn how to find the determinant of a square 3 by 3 matrix. And once we've learned that, then we can use Cramer's rule, because Cramer's rule uses determinants. So, what is a determinant? It really got its name determinant because primarily, or maybe not primarily, but one of the things a determinant does is determine whether or not a matrix has an inverse. It determines whether or not a matrix, a square matrix, has an inverse. A determinant is just a number that we calculate from the matrix using a specific process. Each matrix has its own determinant that's unique to that matrix. And when we calculate the determinant using the method I'm about to show you, depending on the value of the determinant, we can determine whether the matrix has an inverse. We can also use that to solve systems of equations. There are also other things to be done with a determinant that we're not going to learn yet, or we're not going to learn at all in Math 1050. You learn them in physics and other disciplines. So for our intent and purpose, we're going to use it to determine if a matrix has an inverse and use it in Cramer's rule to solve a system of equations. Now the notation for determinant here, determinant of A, or here it does resemble absolute value notation. It is not absolute value. When we're talking about a matrix, those two vertical bars denote determinant. So starting with a 2 by 2, and hopefully when you see this you're going to recognize we've actually done this already in section 6.3 when we found the inverse of a 2 by 2 matrix. So given a 2 by 2 matrix here, A, B, C, D, then, and I've given 3 different notations. You can either write it as determinant of A or determinant of A, or even this. You notice, and this is a subtle difference, but it's something you need to pay attention to. It looks like I've just rewritten the matrix, but notice I've used vertical bars here rather than matrix notation. So those vertical bars denote finding a determinant. But the determinant of a 2 by 2 matrix is calculated using this formula, AD minus BC. It's this product, AD, minus that product, BC. And if you're thinking that looks familiar, it does, because of the inverse. So the inverse, if you remember from the last lesson of a matrix, 2 by 2 matrix, was 1 over AD minus BC. Then we switch the place of D and A, and B and C switch sign. But what I'm getting at here is that denominator there is just a determinant of A. So some textbooks actually switch the order and do 6.4 determinants before inverses so that they can write the inverse formula as 1 over the determinant of A times that matrix. So anyway, that's where we've seen it before. So a 2 by 2 matrix determinant, very easy to calculate, very quick. So for example, find the determinant of A. So we calculate this first product there, 3 times negative 4. Then we subtract this product here, negative 2 times 8. So this is negative 12 minus negative 16, or negative 12 plus 16, which is 4. Let's try it again here. First we have this product here, A times D, so that's negative 2 times negative 9. Then we subtract this product here, 3 times 6. So we have 18 subtract 18 equals 0. Now, this we need to take note of. When the determinant of A equals 0, then the inverse of A does not exist. Reason being, going back to what I just had, probably should have left it on there, but if we're talking about the inverse formula, it's 1 over the determinant of A times this, oops, that's opposite of B, opposite of C, there we go. So if the determinant is 0, we'd end up with 0 at the bottom of a fraction. Can't divide by 0, therefore this is undefined. So if the determinant is 0, the inverse doesn't exist. That's how we use the determinant to determine if a matrix has an inverse. Is we can first calculate the determinant. If the determinant is 0, then we know it has no inverse. Okay. Now, the determinant of a 3 by 3 is a much, much different process. And unfortunately does take a little bit longer. So, in order to show you this process, we need to define a couple of things. We need to define what's called a minor and a cofactor. Now, let's take this 3 by 3 matrix here. Let's say this is matrix A. A minor matrix is going to be denoted by a capital M, and then it has two numbers here that represent a row and a column. So if I'm talking about M1, comma 1, that means row 1, column 1. So here's what you do to find the minor. If it's minor M sub 1, comma 1, then you cross out that row and column. So in this case, it's row 1, column 1. I'm going to cross out row 1, and I'm going to cross out column 1, leaving a smaller matrix down there in the bottom right corner, that's called the minor. It's a minor matrix. So if I write 2, 4, 5, 6, that's the minor there. And then it's not just the matrix itself. A minor is actually the determinant of that matrix. The determinant of that, we're going to get this product, which is 12, minus this product, which is 20, and we get negative 8. So let me show you another one. If we do a minor 1, 2, what that means is row 1, column 2. So let me so we had 2, 0, negative 2. And then 2, 3, negative 1. There we go. So for 1, 2, this one here, we would cross out still row 1, but now we cross out column 2. And you can see that leaves those 4 numbers there. So that would comprise that smaller matrix. So it was 0, 4, negative 2, 6. Then we find the determinant of it. So it'll be that product there, which is 0, minus that product there, which is negative 8. 0 plus 8 is 8. Okay, and again, just for the sake of practice, let's do one more. If we did this one now, minor 1, 3, that means still row 1, but now column 3, which leaves those 4 values. So those are the 4 values which would comprise this minor. 0, 2, negative 2, 5. Then we find the determinant. So that product is 0 minus this product, which is negative 4. 0 plus 4 is 4. So those are called minors. Minors are found by crossing out a row and a column, a particular row and column. So that's what a minor is. Now, cofactors really all a cofactor is a minor, which are these values here. These are all minors. A cofactor is just a minor that's been multiplied by either 1 or negative 1. So once you calculate the minor, to find the cofactor, you either multiply that minor by 1 or by negative 1. So, and the way you determine whether to multiply it by 1 or negative 1 is based on this pattern right here. If the number, well, let me just show you rather than try to explain that right now. Let me show you what I mean. So the capital letter M denotes minor. The capital letter A here denotes cofactor. but a cofactor is just a minor that has been multiplied by 1 or negative 1. So going back 1 comma 1, 1 comma 2, 1 comma 3. So going back using the same 3 by 3 matrix that we just used. Now also I want you to copy down this pattern matrix of plus minus plus. This first one here, the capital letter A means calculate the minor in 1 comma 1, which means row 1 column 1, which we did. Here we calculated row 1 column 1, which left this, which we calculated here to be negative 8. So I'm going to go ahead and write that right here for A 1 comma 1. The minor was negative 8. And now here's where we either multiply it by 1 or negative 1. The row and column that we crossed out intersect right here in that spot. 1 comma 1. 1 comma 1 has a positive in that spot, which means positive 1. So that cofactor then is going to be multiplied by positive 1, and we get negative 8. So it doesn't actually change the minor because we just multiplied it by 1. So really a cofactor is either just going to change the sign to positive or negative, depending on if you're multiplying it by positive 1 or negative 1. So the second one here, this cofactor 1 comma negative 2, we found that cofactor already, we found the minor already, 1 comma 2. So the minor was 8. But then if we cross out row 1 and column 2, then that intersection point right there, 1 comma 2, has a negative sign. So that means we're going to multiply that minor now by negative 1 because there's a negative sign there. So the cofactor 1 comma 2 is actually negative 8. Now for this one, cofactor 1 comma 3, the minor for 1 comma 3 we already found. It was here. It was 4. And then to make a cofactor, we have to multiply it either by 1 or negative 1. So row 1, column 3 intersects here. There's a positive, which means positive 1. So that's going to be multiplied by positive 1, and it stays 4. So those are called cofactors. We have minors, we have cofactors. Very much related. Cofactor is only slightly different than a minor because it's being multiplied by 1 or negative 1, depending on these patterns. So now that we have all of that, the determinant of a 3 by 3 matrix is found using cofactors. So we're going to use this same matrix that we've been using, 3 by 3. You choose any row or any column. Once you've chosen a row or column, you calculate all cofactors for that row or column. So it's going to be 3 cofactors. And then you find the sum of cofactors so I've chosen, as an example, it looks like I've chosen the top row right there. 2, 3, -1. And I just chose at random. You can choose any row, you can choose any column. I could have chosen that middle column, I could have chosen this bottom row. Doesn't matter which row or column, but just for the sake of this example, I've chosen the first row. So what happens now is we calculate a cofactor. So starting at the beginning of the row, right here, I cross out the row and the column. That left me with this, which you can see I've written here. And then the minor is the determinant of that. So I've written it using determinant notation rather than matrix notation there with the vertical bars. And then one slight difference here is the cofactor, which is this, is now going to be multiplied by a scalar. And that scalar is simply the number where the row and column intersect that you crossed out. So I crossed out row 1, column 1. The number in that entry of row 1, column 1 is 2. So now I still calculate the cofactor here, but then I multiply it by that number there. So 2 times that cofactor. And then I move on and find the next cofactor across that row. So I already found the cofactor here, so now I move across the row and find the cofactor here. So if I cross out that row and column containing that, I put the number here, the number there was 3, and then I have the minor that results there. And to make it a cofactor, notice how I've changed it to -3, because up here it's +3, but here I made it -3, because if you remember that pattern, to make it a cofactor, it's plus minus plus. So in that spot there, which is where that 3 is, I have to multiply it by -1. So -1 times 3 is actually that -3. That's why I put that negative there. Okay, now that I've found the cofactor in this spot, I've got to move across the row and find the cofactor here in that spot. So cross out the row, cross out the column. That leaves that matrix here. Now I find the minor by calculating its determinant, and then I multiply it by the number that's in that spot, which is -1. That's why I've got the -1 there. And then to find the actual cofactor, you have to multiply it by either positive or -1. So since it's a positive there, I multiply it by +1 right there. +1 times -1 still keeps it -1. So I take that scalar, and then I calculate this determinant, which we've already done. The determinant way up here for that row 1, column 1 was -8. But we can show it again here. That product there is 12 minus that product there, which is 20. Okay, now we move on here. We have -3 times this determinant, which is that product 0 minus that product, which is -8. And then we add -1 times this determinant, which is that product 0 minus that product, which is -4. So we have 2 times negative 8 minus 3 times 8, and then plus negative right there is minus 1 times 4, which is negative 16 minus 24 minus 4, which is negative 44. So the determinant for that matrix is negative 44, and it would be negative 44 regardless of which row or column we chose to expand to find the three cofactors. To show you what I mean by that, let's do the exact same matrix using another row or column. So let's try this middle column right here. 3, 2, and 5. So if I'm going to use this column here, then I've got to find a cofactor for each entry there along that column. So for the first one, for this 3, I'm going to cross out the row and column there. So 3, and then the minor is 0, 4, negative 2, 6. Now that's the minor. The cofactor now, if you remember, plus, minus, plus, minus, plus, minus, plus, minus. There we go. Since we're expanding along that column there, that very first entry has to be negative, or we have to multiply it by negative 1 rather. So I've got to multiply that there by negative 1, which makes it negative 3. Okay. Now, moving down to this entry, 2, if I cross out the column and the row containing that 2, then the minor left over are these 4 values, 2, negative 1, negative 2, and 6. And then I check to see whether I'm going to be adding or subtracting, or whether they need to multiply that by 1 or negative 1. That 2 is in this spot. I multiply it by positive 1, which means it stays positive 2, so I'm going to add it. Finally here, for that entry, I have 5. If I cross out the row and column containing that 5, then the minor would be the determinant of 2, 0, negative 1, 4. And then I need to check whether to multiply it by positive negative 1. 5 is in the same spot where that negative 1 is, so I need to multiply it by negative 1, which would change it to negative 5. Now, I calculate all of these determinants. This is 0 minus that, which is negative 8, so minus negative 8. That product is 12 minus that product, which is 2. And here we have this product, which is 8 minus that product, which is 0. So we have a negative 3 times 8 plus 2 times 10 minus 5 times 8. So negative 24 plus 20 minus 40 is equal to negative 4 minus 40, which is negative 44. Okay. One more time. This process is actually going to be much, much easier if you can choose a row or a column that contains zeros. Well, let me rephrase that. Not that it's easier, it's just shorter. You may not have to compute all of the cofactors. So one last time, I'm going to now expand along that column because it has a 0 in that second spot right here. So if I'm going to expand down that first column, I'm going to cross out row 1, column 1, which would mean I've got 2 multiplied by the minor matrix, or the minor 2, 4, 5, 6. And since it's in that first spot, I multiply it by positive 1, so it stays positive 2. Now, the next entry would be this entry, so I would cross out the row and column, and I'd have to multiply it by negative 1, so it would be minus 0 times 3, negative 1, 5, 6. Here's the thing, 0 times that determinant, is just going to be 0, so we don't need to bother with that cofactor in the middle, which is why it's recommended that you choose a row or a column that contains zeros. Now moving on, I now go to that negative 2 and cross out the row and column for negative 2, leaving 3, negative 1, 2, 4. Now to finish her off, we calculate these determinants. So this is going to be 12 minus 20. Don't need to do that one because 0 times anything is 0. Minus 2. And then it's going to be 12 minus negative 2. So 2 times negative 8 minus 2 times 14. So we have negative 16 minus 28, which is negative 44. So this is a way to calculate determinant of a 3 by 3 matrix. This is the typical way shown in most college algebra textbooks. Not to beat a dead horse, there is an alternate way to find the determinant of a 3 by 3 matrix. If you follow along in our textbook, you won't see this method in our textbook, but it is a way that will work to find any determinant of a 3 by 3 matrix. So alternate method for 3 by 3 determinant. Let's go back to the one we just did. Okay. So I'm going to write this in determinant notation now. 2, 0, -2. You notice I'm using those vertical bars that look like absolute value. What you do now is copy the first two columns over to the right. So 2, 0, -2, and then 3, 2, 5. So I've copied the first two columns to the right side. Okay. Now I'm going to find products, product meaning multiply, along a couple of diagonals. And it always has to go in this order, starting at the very most top left, so row 1, column 1 there, starting there, you find the products along that diagonal, and then this diagonal, and then that diagonal. So always starting from the left, going to from the top left, going to the bottom right. So with this diagonal, you have 2 times 2 times 6. 2 times 2 is 4. 4 times 6 is 24. And then for this diagonal, it's 3 times 4, which is 12. 12 times -2 is -24. And then this diagonal is -1 times 0 times 5, which is 0. Now it's important to remember that every product found that I've done in red, when you go from the top left to the bottom right, those always add together. Okay, now we find, going from top right now to bottom left, you find this product, and that product. So this one here is -1 times 2, which is -2. -2 times -4 is 4. This one here is 2 times 4, which is 8. 8 times 5 is 40. And then this one here is 3 times 0, which is 0. 0 times 6 is 0. It's important now to remember that any of those that I've done in blue that go from the top right to the bottom left, those you always subtract. Now we find the sum of all this. 24 minus 24 is 0. 0 plus 0 is 0. 0 minus 4 is -4. -4 minus 40 is -44. -44 minus 0 is, hey, look at that, -44. That's an alternative way to find the determinant. And I'm sure you're all saying, why did we not start with that one? It I suppose appears to be quicker. The not a drawback, but word of caution I have seen with this particular method is students will rush through it thinking, oh, this is quick, this is easy. They'll make simple mistakes just because of arithmetic errors. And honestly, with practice and with a little bit of confidence, this method over here can also be very, very quick. Just takes a little bit of getting used to. I don't care which method you use. You can use the cofactor method over here, or this method of multiplying along diagonals. So either way, it's going to give you the same determinant. Okay. Last part of the lesson. Cramer's rule can be used to solve a system of equations, and it's a method that uses determinants. So you can see there I've got a system of linear equations in two variables. So what we would do is calculate, for two equations like this, we would calculate 3 separate 2 by 2 determinants. And if you remember, 2 by 2 determinants are very quick. So Cramer's rule for a system of two equations is actually very simple and very quick to do. The first determinant here, which I'm going to call D, is just a coefficient matrix. So you take all the coefficients in front of the variables there and you form a matrix. Okay. The next matrix I've written with a subscript of x to help you remember. This applies to the x column, or the coefficients in the x column. Notice I've taken out the coefficients in the x column, a and c, and replaced them with these values here. So d sub x, these values just replace the coefficients that were in front of x. Okay? So replace the first column of d with r and s. Now the last one, d with a subscript of y, and use a subscript of y to help you remember that it's in the y column or the second column. You replace the coefficients b and d with the values r and s. So they go right there in the second column. So those are the three matrices. We have d, then d sub x, and then d sub y. So once you have set up those three matrices, the value of x is the determinant of this matrix divided by the determinant of that matrix. And then the value of y is the determinant of this matrix divided by the determinant of that matrix. So like I said, as long as you're proficient in finding the determinant of a 2 by 2 matrix, then using Cramer's rule to solve a 2 by 2 system, or a system of two equations, two variables, can go pretty quick. So we have an example here. Solve this system of linear equations using Cramer's rule. So we need to set up a couple of, so the coefficient matrix would be 2, 1, 6, 8. And then while we're at it, let's just go ahead and calculate the determinant. Remember, it's that product there, which is 16, minus that product there, which is 6, so it equals 10. Next one would be a matrix where the coefficients that were in the x column are going to be replaced with these values here. So in the first column it would be negative 1 rather, and 2. Second column just keeps those same values, 6 and 8. So then the determinant of d sub x is that product, which is negative 8, minus that product, which is 12, so that's negative 20. And finally, d sub y, now it's the y column here, or the second column, that's going to have those values of negative 1 and 2. The first column is going to have the same values as it originally did there, 2 and 1. And then the determinant would be that product, which is 4, minus that product, which is negative 1, That equals 5. So according to Cramer's rule, then, the value of x was the determinant d sub x divided by the determinant of d. So the determinant of d sub x was negative 20. The determinant of d was 10. So that equals negative 2. The value for y was the determinant of d sub y divided by the determinant of d. So the determinant of d sub y was 5. The determinant of d was 10. So we have 1/2. So the solution to this system of equations was negative 2, comma 1/2. And if we, as always, good idea to check answers. For example, if x was negative 2 here and y was 1/2, we have negative 2 plus 4, which is 2. Looks like it checks out there. We could also check it in that top equation, but it would work also in that top equation. So that's Cramer's rule for 2 equations, 2 variables. Let's have you try it again here. Go ahead and pause the video. Try to find, using Cramer's rule, the solution to this system of equations. So hopefully what you found is, I'm just going to go ahead and, rather than writing things twice, the determinant of d is going to be the determinant, the coefficients, which is 42 minus 48, which is negative 6. The determinant of d sub x would have been the determinant, you'd have the 33 and the 20 here, the 12 and the 7 stay there. So 33 times 7, let's see, 33, 7, that's 21. 21 plus 2 is 23, 231. Minus 20 times 12 can be 240, better check that. $240. So that's negative 9. And then d sub y, the determinant there. Now the y column, or the second column, is going to have 33 and 20. X column is going to be the same, 6 and 4. That determinant is 6 times 20, which is 120, minus 4 times 33, which is 132, let's see, 12, 13, yeah, 132. So that is negative 12. So now x is equal to determinant d sub x, which is negative 9, divided by determinant of d, which is negative 6. So we have 3/2. Y is equal to the determinant of d sub y, which is negative 12, divided by determinant of d, which is negative 6. So we get 2. So the answer, or the solution to the system of equations, is 3/2, comma 2. And just to verify, never a bad idea, 6 times 3/2 plus 12 times 2. 6 times 3/2 is 9. 9 plus 24 equals 33. Now, Cramer's rule can also be applied to equations of, or systems of three equations, three variables. You would just have one additional determinant d sub z. So you'd actually be finding four determinants: determinant of d sub x, determinant of d sub y, and then determinant d sub z. And then the same rule would apply. X would equal dx over d, y would equal dy over d, and then z would equal dz over d. Not actually going to take the time to show you here in the video, but it would be the same process, just finding four different determinants of a 3x3 matrix. So that should finish up lesson 6.4.